Hello everyone, my name is Hong Li. It is my honor to have a chance here to present our paper boosting multimodal model performance with adaptive gradient modulation. Multimodal learning is a fast-moving research area regardless of the exciting advancement. People still lack understanding the mechanism of how the model make use of information from different modalities. A multimodal situation is hard as the interaction and computation among different modalities complicates the model's response. A recent work demonstrates that the modality computation can be helpful for a multimodal model without yielding suboptimal performance. To resolve this issue, researchers devised a variety of methods to modulate the training process of a multimodal model to improve the model performance. However, those methods are largely limited to late fusion cases and cannot be generalized to more complicated model architecture. It is natural to ask, can we design a modulation method that applies to more complex fusion structures? Furthermore, is it possible to understand the work mechanism of the modulation in terms of modality computation? To address these two challenges, we first draw inspiration from game theory and propose adaptive gradient modulation method that can boost the performance of multimodal models with various fusion structures, different modality types, and different model architectures. Moreover, we introduce the model concept to capture the computationless state of the modality and build a novel metric to directly measure the modality computation stress. Based on the above, we systematically analyze the behavior of modality computation and study the mechanism of how our modulation method works. Now, we present details of our proposed adaptive gradient modulation method, or AGM in short. The basic idea is that we need to estimate the contribution of each individual modality to determine whether its information has been sufficiently exploited. For those overused modalities, we need to suppress their supervision signal, while for those underused ones, we shall enhance their supervision signals. There are two key components in AGM, namely sampling module, which estimates the monomodal contribution, and the description ratio module, which determines the modulation stress of an individual modality. The sampling module builds upon the sampling value from cooperative game theory. In our situation, we identify the multimodal model as the game's value function and involve the modality as the players. Applying sampling value enables us to isolate contribution from individual modality in complex situations such as early fusion and hybrid fusion cases, analyze base for our modulation algorithm and further analyze. Next, we move on to the description ratio module. This module attempts to regularize how the model uses each modality based on the amount of information carried by each modality and the current iteration. Specifically, we use the difference amount of information of a modality relative to other modalities to represent the current state of this modality in the multimodal model. The target is to tune the current state towards a reference state, which is estimated using corresponding running average monomodal cross-interface. This modulation could elevate model computation and improve the use of information by the model. In addition to AGM algorithm, we also exploit the mechanism underlying the computation through a novel metric. The key step is to estimate the computationless state of a modality in a given multimodal model. To this end, we introduce monomodal concept to capture a model response without computation. Then, the derivation of normal response from their monomodal concept shall directly measure the computation stress of each modality. In this work, we adopt a linear probing method to quantify this deviation. To fully evaluate the effectiveness of our proposed AGM algorithm, we carried out an extensive experiment of different combinations of modalities on different tasks using different fusion structures and with different model architectures. The following tables compare the performance after applying AGM with other modulation methods as well as the short training using different situations. Our experiment includes those on awareness and quality dataset, which has the two modalities. and those on your finding dataset with the 3 modalities. Moreover, we also test on the more sophisticated hybrid fusion case on the AVG and MOSI dataset. Evidently, AGM works well on all cases, effectively improving the model performance. In addition, we have monitored the training process, compared with the behavior prediction accuracy and the computation stress with and without AGM. It is demonstrated in the figure that AGM can elevate the modality computation in a multimodal model, makes it relies on more informative modalities, hence improves the model performance. In conclusion, we propose an adaptive gradient modulation method that boosting the model performance regardless of fusion strategies and the number and the type of modality involved, the network. Moreover, the modulation pushes the model to rely on more informative modality, while a high-order effect exists when multiple modalities are present. Thank you.